we've got two situations depicted here. One, a pendulum hanging freely, and a car on an incline. Let's start with the car on the incline. I've got the delta S vector. Now, what I want you to do is sketch the weight vector. Estimate its projection on the delta S vector. You should pause the video and do that. But I'm going to continue, so I'm not going to wait for you to do that as I would in class. Okay, you should have paused the video by now and done that. Now, you don't know how long to draw the weight vector. Let's just draw it at some reasonable length. Okay, so here's the weight vector, lowercase w. Now we want to project the weight vector onto delta S. You should then sketch the delta S vector and the weight vector, probably someplace other than this sketch. And I'll say that you should have sketched this. You should have drawn this sketch, and then proceeded accordingly. Now, if you haven't, you get it into your brain better if you sketch it. But if you've done a lot of sketching of this sort of thing, okay. Now, how do we project the weight vector here on the delta S vector? You should pause and do that if you haven't already, using a picture similar to this. Now, you might have drawn the weight vector longer or shorter. That's okay. I'd want to draw it fairly long so that we can kind of see the projection. But you don't want to draw it too long. You overwhelm the delta S vector to do that. Okay, well, you should have done that. Okay, here's the extension of the delta S vector, and we come back here at a right angle. I'm probably not going to do a real good job of this because I don't have a good angle on the board, but the projection line is going to look something like this. So here is our W parallel vector. Okay? And I didn't ask you to estimate the W parallel vector as a proportion of W, but I'm going to ask you to do that in a minute. Now let's say that I want you to estimate W dot delta S if the magnitude of W without the absolute value sign, is for that cart, let's say it's a heavier car than we've been using. Let's say it's 200 newtons, and delta S equals 1.5 meters. Okay? Now, you should do that estimate, but I'm going to go on with it, so you should pause and do that estimate. Now I'm assuming you've paused and done your estimate. Okay, if this is 200 newtons, how big is this? Clearly less than half of 200 newtons. Okay, probably around a quarter or a little more than a quarter. So I'm going to say our estimate W parallel is, let's say, no, I don't like 6, that's too big. It's less than a third. I'm going to say 55 newtons. Okay? Now, if you come out anywhere in that vicinity, you made a good estimate. If not, I might question your estimate, but you might have drawn the picture just a little differently than I did. We're not measuring these angles. You don't have a copy of this picture. So just make sure your estimate is reasonable. So that's the magnitude of W parallel. Now, we're trying to estimate the dot product. You should do that, but pause, do that, but here's the dot product. Okay, so from this, picture we get this, and from this we're going to get W dot delta S equals W parallel dot delta S, which equals the magnitude of W parallel times the magnitude of delta S times the cosine of theta, where theta is the angle between W parallel and WS, W parallel and delta S, and that's going to be 55 newtons times 1.5 meters times the cosine of 180 degrees, because delta S is in this direction, W parallel is in this direction. And that's going to equal negative, and let's see, half of 55 is 27 and a half. We add that, we get 92 and a half Newton meters, or negative 92.5 joules. Now, what's the meaning of this? And why should this make sense? Well, we notice that W is acting this way, delta S this way, and the parallel component of W parallel is, or the parallel component of W, the component of W parallel to delta S is down the incline. So if we go up the incline, our displacement is up, our force is down, so the force and the displacement have opposite signs, and it follows that the force times the displacement has to be negative. Okay? Negative work is done on the car by the weight force. Now, the only way we have a delta S here, there are two ways. I could be pushing the car up the hill, or the car could have enough initial velocity to travel the displacement delta S. In the case where the car is coasting and has enough velocity to travel through this displacement, then this is going to equal the change in the car's kinetic energy. So for a coasting car, delta KE would be 92.5 joules. That is, provided there's no other force. Now, if there are other forces, for example, friction, then the delta KE would not be negative 92.5 joules. The reason being that the net force would not be just W. Okay, W is not necessarily the net force. In the simplest case where we can ignore friction and there are no wind resistance, nobody pushing one way or the other, nobody throwing eggs at the car, the net force would be the resultant of the weight in the normal force, which is just the parallel component of the weight. Okay? In any other case, might not be so.